So today we are starting our last module of this course, and that is on oscillations and waves. When we talk of oscillations, what do we have in our mind? Some object which is going from one place to other place, coming back to the first place and then repeating that path. That is what we call oscillations. Pendulum is the simple example. So I have this pendulum for example. So you have a string, you have this bob. Position of this pendulum, that is the quantity which will change its value. So here there is a position, then when it oscillates it goes here, another position, it goes here, another position, it goes here, another position. It goes up to some extreme and then it traces back those positions and comes to the first extreme. So that is how it oscillates. We say that it oscillates. It goes from one position to the other position, retraces those positions back, and then whole thing repeats. That we call oscillations. We have many oscillating systems that we encounter in our life. I have here 2, 3, 4 things. Let me show them one by one. Here I have put this spring, and through this spring I have suspended some weight, some mass here. Okay. Now if I pull this down and release, then the position of this mass will change periodically between one extreme and the other extreme, and we will have oscillations. Another system, we have this toy. We have this toy and its head is the system, and if you displace the head from here and release, see how it oscillates. It goes from one extreme to the other extreme and then retraces the path. So this is oscillations. Another system, we have this bulb, filament bulb. If I put it here, on the table, and then if I displace it slightly from this position, see how it changes. It goes to this side, goes to this side, goes to this side, goes to this side, goes to this side. So it is oscillating. The position or angular position is changing with time between one extreme and the other extreme. More examples, I have a beaker here, and there is water here, and I have this vessel, small vessel, and if I put this in this water, see what happens. It floats. And then if I press it down, it will oscillate. Look at it. There are two kinds of oscillations, if you can note. It oscillates in angles like this, and it also oscillates up and down. Then I can show you this swing. You are familiar with this. We used it in our electricity magnetism module. This is also oscillations. It is oscillating. The swing is oscillating. And I have another system. I have this blade, this hexa blade. On that blade I have put some mass here. We will be doing more experiment with this later. But here, if I again displace it from its equilibrium position and release, it oscillates, goes from this position to this position and then retraces those positions back and so on. So, this is oscillating. Now, for oscillations, it is not always confined to material things moving. Oscillations can be of anything. Oscillations can be of electric field, magnetic field. They oscillate. That means the value of magnetic field changes from one particular value to another particular value and then retraces those values as a function of time. We say electric field oscillates. Similarly, magnetic field can oscillate. In our light, electromagnetic wave, electric field and magnetic field do oscillate with a large frequency, 10 to the power 15 times per second or so on that order. So, this is also oscillation. The field is the quantity which changes its value as a function of time, and that change is between two particular values, and then periodically it goes from one extreme value to other extreme values and then retraces all those values as a function of time. Time is continuously increasing or is going, and this value changes. So, that is oscillations of electric field or magnetic field. You can have many other things oscillating. You can have oscillating current. You have alternating current. So, what is happening there? The voltage oscillates from some value V naught to minus V naught. So, it is an oscillation of voltage or oscillation of currents. You can have oscillations of purely abstract quantities. You all know sin x, cos x, tan x and all those functions, trigonometrical functions. They oscillate. The value of sin x, as x changes, x continuously, you increase x continuously. And what happens to sin x? It will oscillate between plus 1 and minus 1. From plus 1, if x increases, it will take all values up to minus 1, and as x increases further, and it takes all those values back to plus 1, and this will continue as x keeps on increasing. So, that is the kind of oscillation we have in mind. First, we will do some oscillations with the mechanical systems where some material will change their position as a function of time. We will learn the equations, we will learn the terminology and all that, and we will extend it to some other quantities oscillating. For example, if you take this spring mass system here, it is in equilibrium and this is a stable equilibrium. If I pull it down, it will go up. If I push it up, it will go down. This is an essential condition for any oscillation. You must have a stable equilibrium position, only then around that it can oscillate. If I push it up, it goes down. If I pull it down, it goes up. That stable position is essential, and stable equilibrium means minimum of potential energy. So, that is a test, or that is a condition. The potential energy should have a minima somewhere, only then around that position this thing will oscillate. So, this minimum of potential energy, that depends on the kind of forces which are acting. If you have gravitational force, you have gravitational potential energy. If particle goes down, the potential energy decreases. If particle goes up, the potential energy increases. If you have springs, you have elastic potential energies, half kx square type. So, if the spring is compressed or it is extended, the potential energy correspondingly increases, or there may be several forces. In a solid you have molecules, and these molecules are bonded to each other. So, those forces, those electromagnetic forces which are there, which keeps this solid in its shape, that also has corresponding potential energy, and for a particular separation between two molecules, that potential energy is minimum, and then that is the stable equilibrium separation between the molecules. If somehow these molecules go closer, then these forces will take them apart. If they go farther apart, these forces will bring them down. So, they can vibrate. So, that is a kind of oscillations that we have thermal, because of all that thermal energy. We have oscillations in the molecules of the solid. All these things come because of that minimum of potential energy. The basic equation for an oscillation is something like this. If you have a particle of mass m, if I write the acceleration as a, this is equal to negative of kx. So, what are the things? I am talking in reference to a particle whose position is given by x and the acceleration is given by a. That means, if you have position as a function of time, you can tell what is the velocity, and if you have velocity as a function of time, you can tell what is the acceleration. So, this is the basic equation. I am focusing on the mathematical structure because similar mathematical structure will be applicable to oscillations of varieties of different kinds. Okay. So, this I can write as acceleration is say rate of change of velocity, which we write dv dt. So, it is m dv dt equal to minus kx, and as acceleration is rate of change of velocity, velocity itself is rate of change of this position, and so this v can also be written as dx dt. Rate of change of position is velocity, and rate of change of velocity is acceleration. So, these are some rules of calculus. If you know x as a function of time, how you can get velocity as a function of time, and if you know velocity as a function of time, how you can get the acceleration as a function of time. So, there are certain rules, but it is like this. And if I put this thing here, the way it is written is m, this is d dt of dx dt. In place of this v, I am writing this thing is minus kx, and this is written as d2x dt square. And if I bring this m here, it is minus omega square x, where omega is square root of k by m. Alright, so this is the kind of equation that we have. This is the basic equation for oscillations. Your acceleration, this whole thing is this big d2x dt square is nothing but acceleration. Acceleration is negative some constant, positive constant times x. This is the basic equation. If a system follows this kind of equation, then this x will oscillate in time, and you can write this x from here. In this situation, you can write this x as some constant times some cosine of omega t, or omega t plus phi, or sine omega t. This kind of dependence of position on time will result if you have this basic equation. And if that is the case, this is known as simple harmonic motion, right? This kind of motion is known as SHM, simple harmonic motion. And in any case of oscillation, if you have a minimum of potential energy. For small oscillations, this situation will occur, because this also demands, this kind of thing also demands that your potential energy is of this kind, something like some k x square or x minus x naught square of this type, this parabolic type. So even if it is not parabolic, suppose it is not parabolic, it is u here, it is x here, and then it is something, this is the point where you have a stable equilibrium. It's not of this type, but if I concentrate for a small oscillation only this much of the part, then yes, then I can approximate it as a parabolic curve, and therefore for small oscillations, all varieties of oscillations for small amplitudes, this equation is followed to a good approximation, and that is why it is important. Now this equation tells that as time passes, the amplitude does not decrease, because this cos omega t will always go from plus 1 to minus 1. So x will go from plus a to minus a. So it is a constant amplitude oscillation for all time to come. Real systems are never like this. If you take this spring mass system, if I oscillate it with some certain amplitude, you wait for some time and you will find that the amplitude is decreasing, gradually decreasing. This is because there are several dissipative forces. You have air which is exerting force on this, there are some internal frictional forces. So because of these dissipative forces, the amplitude always decreases as a function of time in a real system. So how do we manage that in our equations? And the only thing we have to do is we have to add this dissipative forces here in the equation. So mass time acceleration is this force which we call restoring force, because it tries to bring the system in that stable equilibrium position. So this is known as restoring force. Together with this, we should write those dissipative forces, and then you will again, if I do the mathematics, I get certain equation. What kind of dissipative forces we will be adding? So one is that you add a term minus some constant times velocity. Quite often this resistive force is proportional to velocity, so you can add that, and if you add that, then this changes. How does it change? Some kind of exponential, some minus beta t type. This term is this comes here, this factor comes here, and then your amplitude will be continuously decreasing. So actually there is some approximation involved. This frequency will be slightly changed, but for small damping it is almost the same. So we will go by that. So now let me take an example from a totally different area, and that is from electrical circuits. Here I have a capacitor, the capacitor that we used earlier. This is that 1 millifarad or 1000 microfarad capacitor, and here is the solenoid. This also we have used earlier. Now suppose I charge this capacitor by connecting this battery terminal to the capacitor. I charge this capacitor. Now the capacitor is charged. Now if I connect it to this solenoid, what will happen? When I connect this to the solenoid, the circuit is complete. You have positive and negative charges here. So the charges will flow and finally it will be neutralized. But when charges flow through this solenoid, the current will build up in the solenoid, and when current builds up, the magnetic field will be created, and that magnetic field will change in time because the current is building up, and that changing magnetic field will create an induced electric field, and then that field will create its own EMF. So what will happen to this whole system? You have a potential difference here, Q by C. If Q is the charge on the capacitor, C is the capacitance, Q by C is the potential difference, and this side also you have a EMF produced which will depend on how the current is changing with time. So you will have a combination of that, and that will decide how much will be the current. So let me try to write an equation within idealization that there is no resistance. The resistance is negligible. In that case, this potential difference Q by C here should be equal to what induced EMF is generated here. So let me just give you the equation, but remember qualitatively, induced EMF is proportional to the rate of change of this current, because that decides how the magnetic field is changing, and the rate of change of magnetic field will decide the induced electric field, and that finally will decide the EMF. So we will have this equation, this Q by C. Q by C, what is that Q by C? Q is the charge on this capacitor, Q as a function of time, and C is the capacitance. So this is the voltage here at the ends of the capacitor, and what is the corresponding part on this solenoid which are connected? This will be minus some constant di dt. What is this I? This is the current here, and what is di dt? Just like this, rate of change of position gives you velocity, we write as dx dt. Rate of change of velocity gives acceleration, we write that as dv dt. Similarly, di dt is rate of change of current. So current is a function of time here, and therefore this rate at which the current is changing, that decides how much will be the change in magnetic field, blah 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 blah, and finally the EMF. So this becomes the equation, and this charge and this current, they are also related. After all, what is this current? Current is flow of charge. So if charge flows, charge on each plate of the capacitor, that magnitude will decrease. So I can also write I is equal to dq dt. And if I write this I here, what kind of equation I am getting? L d2q dt square is equal to minus q over c. So in place of this I am writing dq dt, and when you write that way, d dt of dq dt, just like here, d dt of dx dt, that we write as d2x dt square, and similarly here we will write this as d2q dt square, minus I have put here, so it is minus q by c. If I take this L on this side, I have d2q dt square, this is equal to minus omega square q, where omega is 1 by square root of LC. This L goes here, so 1 by LC, I write that as omega square, so omega is 1 by square root of LC. Now look at this equation, and look at this equation. They have identical mathematical structure. So the charge will oscillate, not physically. The magnitude of charge on the capacitor plates, on the positive plate you have plus q, on the negative plate you have minus q. So this q, the magnitude of charge, that oscillates in time. and that oscillation will be again given by q equal to some q naught, maximum initial charge that you have given, and cos omega t. And similarly the current will oscillate, I equal to I naught and then some sin omega t or like that. So if there is no resistance, this will go on. The charge will go through the capacitor and finally the charge will reverse. But in a mechanical system, always you have some dissipative force. In electrical system, you always have some resistance. So some resistance will always be there. So you have to write in your equation that resistance also. So if you include that R resistance, R times I is the potential drop there. So this will be plus Ri here. Then again your equation will change and you will have some q equal to q naught cos omega t and some e to the power minus beta t or like that. So the charge and hence the current will gradually damp out and finally it will be all 0.